that relate to charge, to pH, to pKa, and a little bit having to do with buffers as well. So the first things that I'll work relate to calculating approximate charges on molecules if I give a pH and pKa values for certain groups. I'll remind you of a couple things that I talked about in class. So first of all, I said that you can, for estimating charge, you can make the following assumptions. The first assumption is that the pH is 1 or more units below the pKa value for a group. Then you may assume, for the purpose of calculating charge, that the proton on that group is on. Conversely, if the pH is 1 or more units above the pKa for a group, you may assume the proton for that group is off. Now, the charge on an individual group will depend upon whether that group is a carboxyl group or it's an amine group. An amine with the proton on has a charge of +1. An amine with the proton off has a charge of 0. A carboxyl group, by contrast, with the proton on has a charge of 0, and a carboxyl group with the proton off has a charge of -1. So a really good problem that illustrates that is number 2 that you see on the screen here. And problem 2, check my thing here. Yes. Problem 2 works with a theoretical amino acid called Ahernium. It says it contains 2 carboxyls and 3 amines. It says the pKa's are, for the carboxyls, number 1, it has a pKa value of 2.2. Carboxyl number 2, it has a pKa value of 4.4. etc. Amine number 1 with 5, amine number 2 with 8.5, and amine number 3 with a pKa of 9.5. So I said predict the charge on Ahernium at the following pHs, and the first pH I said was pH of 1. And so really all that we're doing in these types of problems is applying that rule that I gave you. That's a rule I said you would need to know. I wouldn't give you on the exam, so you would need to know how to determine if the proton is on or off based on what I told you earlier. So for the carboxyl group number 1, the pH of 1 is more than 1 unit below the pKa of the first carboxyl, so that would mean the proton there was on. It's more than 1 unit below the pKa of the second carboxyl, so that would mean that proton is on. It's more than 1 unit below the pKa of the first amine group, meaning the proton again is on, this proton is on, and this proton is on. Now, we say, okay, well, when a carboxyl has the proton on, what is the charge on it? Well, on a carboxyl, the charge is equal to 0. For a carboxyl, it's 0. For an amine, the charge is +1, +1, and +1. Meaning that the overall charge here is equal to +3, and that's exactly what we had right here. If we change the pH to 7, we have to simply apply the rule again and say carboxyl number 1, the pH is more than 1 unit above the pKa, so in this case the proton would be off. Carboxyl number 2, again, the pH is more than 1 unit above the pKa, the proton would be off. Amine group number 1, the pH, again, more than 1 unit above the pKa, the proton would be off. And amine group number 2, the pH would be more than 1 unit below the pKa, so this proton would remain on. And the same thing for amine group number 3, the proton would remain on. In that case, if we do the calculation here, protons off of carboxyls are equal to -1. Off of carboxyl is -1. Off of an amine, the charge is 0. On an amine, the charge is +1. And on an amine, the charge is +1. So the overall charge at pH 7 would be equal to 0, because if we add these up, we get 0. Last, if we had a pH of 11 and we did the same calculation, well, we'd see, first of all, that 11 is above the pKa values of all of the groups by more than 1. So we know that in every case, the protons are going to be off, 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 and off. This, by the way, was 1. This was 7. And this was 11. Okay? So then we just simply apply our rule for our carboxyl, the proton being off, the charge is -1. For the other carboxyl, of course, -1. And for the 3 amines, when the proton is off, the charge is 0, 0, 0. We add those up and we see a charge of +2. So that tells us what that overall charge would be. Okay, So that's how we would determine the charge of a polypeptide chain there. I'm not asking my 350 class this year to determine the PI, so I'm not going to work through that here for you. But if you did, you would get the number I wrote there. The solution is 6.75. Okay, well, the principle that I've illustrated for you here with respect to the charge of a theoretical amino acid is really no different than the type of calculation we would do if we had a polypeptide chain. So for a polypeptide chain, I would have to, of course, give you the pKa values because I said you wouldn't have to memorize those. So I might give you something like this. I might say you may assume that the R group carboxyls are something that has a pKa value of 4.4, that the R group amines have pKa values of, let's say, 11.5. The alpha carboxyl have a pKa value of 2.2, and the alpha amine would have a pKa value of, let's say, 9.0. Okay, so that might be something I would give you on an exam, and then I would give you a theoretical polypeptide chain. It might be something like this: methionine, lysine, leucine, glutamic acid, and last, let's say, serine, something like that. And so I said, okay, here's a polypeptide chain. It's got 5 amino acids in it. And the pH in the first case, we might say, is equal to, let's say, I don't know, for the sake of argument, let's say we have a pH of 10.1. Okay, and so the charge at 10.1 is 10.1 is equal to what? Okay, so that would be a reasonable problem. To calculate the charge of a polypeptide chain, we remember, first of all, that the alpha carboxyls and the alpha amines that go together to make peptide bonds no longer ionize after they've done that. So we don't have to worry about any charges between the amino acids. We do have to consider charges of the alpha amine. We have to consider the charges of the alpha carboxyl, because every polypeptide chain is going to have one of those at each end. And then we have to consider the charges of any R groups that might ionize. So in the case of a lysine, we have an R group amine that can ionize. In the case of glutamic acid, we have an R group carboxyl that can ionize. So now we just simply go apply our rule, as we did before on the previous problem, to calculate the charge of the polypeptide chain that you can see here. Well, in this case, what we would see is that we start, for example, with the R group carboxyl, has a pKa of 4.4. The pH is more than 1 pH unit above it. That would mean that the proton is off of the R group carboxyl. So in this case, the R group carboxyl loses its proton and would have a charge of -1. The R group amine has a charge of 11.5. Its pKa would be above the pH of 10.1. So the pH of 10.1 would be lower by more than 1 than the R group amine. That would mean the R group amine has its proton on, and the overall charge of the R group, oh, that's it, that's the wrong one. R group amine is over here, would have a charge of +1. Okay, now if we go to the alpha carboxyl, the pH is 10.1. It's more than 1 unit above the pKa, and that would mean that the proton of the alpha carboxyl would be off, and so we would have a charge of a -1. And then finally the alpha amine, which I was trying to do earlier, the pH would be equal to 10.1. It's more than 1 pH unit above the pKa. That would mean that the proton would be off of the alpha amine. We would have an alpha amine with NH2 and a charge of 0. So if we added up the charge of this guy at pH 10, it would be equal to 0, +1, -1, -1, for an overall charge of -1. If we did the same calculation and we said that the pH was equal to 3.3, we would just simply apply the rules in the same way. Let's start with the alpha carboxyl this time. We see the alpha carboxyl, pKa of 2.2, pH is 3.3, so the pH is more than 1 unit above the pKa value, which would mean the proton is off of the alpha carboxyl, and it'll be just as before, so it's off here, and the alpha carboxyl retains a charge of -1. The alpha amine, by contrast, has a pKa value of 9. The pH is 3.3. So the pH would be more than 1 unit below the pKa value for the alpha amine. That would mean the alpha amine has the proton on, it'd be an NH3, and we would have an overall charge down here of +1. We would apply the rule to the R group carboxyl. In this case, we see that the pKa value is 4.4, the pH is 3.3. So the pH is more than 1 unit below the pKa value of the R group carboxyl, which would mean the R group carboxyl has its proton on, so it would be that with a charge of 0. And last, the R group amine, pH of 3.3, pKa of 11.5. We would say that the R group amine has a proton on because the pH is more than 1 unit below the pKa value of the R group amine. And so the proton would be on as we see it right here. The overall charge of the molecule at pH 3, or 3.3, would be equal to +1, +2, +0, -1, or an overall charge of +1. So these are the kinds of things that you can apply to the charge, estimating the charge of theoretical amino acids or polypeptide chains. Doesn't really matter as long as you know what kinds of groups you have there, and then apply the rule about the pH relative to the pKa that I talked about before. Okay. Now, if we look at the go back and look at a couple of the solutions that to the questions that I asked about the acids and bases and so forth. What are the pHs of those? I will go through and briefly do those calculations for you. So first of all, what is the pH of a solution of 0.023 molar HCl? We remember in doing this that the pH is equal to the negative log of the hydrogen ion concentration. And yes, that's something I would give you on the exam, that equation right there. That's pretty much a plug and chug right there. pH would be equal to minus log of 0.023. And as far as I'm concerned, that's the only thing I care to see on the exam. Punching in the calculator tells me nothing other than you know how to punch things in the calculator. So I like to see things written out like I've got them written right here. And then you've shown me that you know how to work the problem. In the case of NaOH, we have a little bit different situation. We don't have proton concentration there. We have OH concentration. And NaOH is a strong acid, a strong base, just like HCl is a strong acid. So when I had a strong acid, I had 0.023 molar HCl. It meant I had 0.023 molar protons because every one of them came apart. In the case of a strong base, every one of these guys comes apart, so it means I have 0.18 molar hydroxide ions. And people say, well, what about the sodium? What about the chlorides up here? They don't affect the pH. So get them out of your head. They don't have anything to do with it. All we're concerned about are protons and hydroxides. Well, for calculating the pH of a solution of hydroxides, we would first start by calculating the pOH. The pOH is equal to the negative log of the OH concentration. And the OH concentration we know is equal to 0.18. So that'd be equal to minus log of 0.18. Okay? And the pH, we remember, is related to the pOH in the following way. pH plus pOH equals 14. That's freshman chemistry. And that's also something I would give you on an exam. So therefore, the pH of a solution would be equal to the pOH. I'm sorry, 14. Yep, I can't write there. Would be equal to 14 minus the pOH. I'm going to work down here a little bit. Okay, and that would mean the pH is equal to 14 minus, and I said the pOH was this up here, minus log of 0.18. And again, that would be the solution to the problem. So you wouldn't have to do anything more than that. Okay. Then in the next problem, or part C, I said I had a salt-acid mixture with twice the concentration of salt compared to acid if the pKa is 4.1. So how would I calculate the pH of that solution? Okay. So I've got twice the concentration of salt compared to acid. Well, for that, we know we have a weak acid solution. We remember that it has to be Henderson-Hasselbalch equation. pH equals pKa plus the log concentration of salt over the concentration of acid. And again, that's an equation I would give you on an exam. This would be pretty straightforward. We would say pH is equal to 4.1, which is the pKa that I gave you in the problem, plus the log of, I said it had twice as much salt as acid, 2 over 1, and that would be the answer to the problem. So very simple. In any of my problems that you do, once you get it to the point that you would punch it into a calculator, you are done. And that's all that I have asked you to do. Okay. In question number 4, I said, what is the pKa of a salt-acid mixture if the solution has a pH of 3.3 when there is 3 times the concentration of acid as compared to salt? Okay, so I'm going to leave that up here, and then I'm going to work it down here. I think that all shows on, it doesn't show very well. Let's move it up here. I think that shows, make sure stuff shows on the screen. Okay, so problem number 4 there. All right, so if I've got that situation, then how would I calculate that? Well, I remember again, I always go back to my Henderson Hasselbalch and say that pH equals pKa plus the log of salt over acid. And I'm trying to find the pKa, so let's plug in what I know here. What I know is that I have a pH of 3.3, and that's equal to the pKa plus the log of 3 times as much acid as compared to salt, which means I have 1 salt to 3 acids. So this is pretty straightforward. Also, I would simply rearrange the equation now and say pKa is equal to 3.3 minus the log of 1 over 3. And that would be the solution to the problem. So again, no calculator involved. The 5th problem is another hydrogen ion problem. It says, what is a hydrogen ion concentration of a solution with a pH of 4.3? For this, remember that pH for a solution is equal to, we've already got the hydrogen ion concentration, so we don't have to worry about anything else, is equal to the negative log of the hydrogen ion concentration. And if we take the negative sign to the other side, we say negative pH is equal to the log of the hydrogen ion concentration. And then we take 10 to the power of each side, so we say 10 to the minus pH is equal to the hydrogen ion concentration. And that would tell us then, we already said the pH was 4.3, 10 to the minus 4.3 equals the hydrogen ion concentration. And again, you would have worked the problem. So these types of problems, I think, become very simple if we're manipulating numbers and we are not getting lost punching numbers into calculators. So your challenge is going to be to write them into a form that, like I've done here, so that you show me what you would punch into a calculator. If you punch it into a calculator and you get the number wrong, then you're just going to be wrong. And so that's one more place for you to have error. And I would much prefer to see you write problems where you're actually showing me what you know and showing me how you would go through and solve those problems. I also recommend to students, especially, that you spend some time organizing your work and labeling your work. Students always want to get partial credit when they do problems. But I can tell you from being a grader and from working with graders for many years that you can't give partial credit where people don't label things. The grader can't read your mind, and we won't. So if you don't label your work and you don't show us what's on there, then it's really impossible for us to give you partial credit if you get something wrong. So a word to the wise, label your work and you'll be in good shape. I hope that's helpful, and good luck on your exam.